Hello and good morning for all attendees and followers. I am Dr. Yassine Slimani. My origin is from Tunisia, and currently I am working at the Institute for Research and Medical Consultation at Imam Abdul Rahman bin Faisal University in Saudi Arabia. My main current research activities cover superconductivity, magnetism, advanced and various kinds of advanced nanomaterials. We are working also on energy storage systems. As application, we are interested in energy, technological, biomedical, and environmental application of all these kind of materials. For the talk of today, I decided to present some of our recent works within the field of superconductivity, particularly of high temperature superconductors. So this talk is entitled Improvement in the Performances of High Temperature Superconductors. In this talk, we will present the importance of superconductivity in our life and their main important applications. After that, we will describe the fundamental properties of superconducting materials, the limitation in this field, especially the problematic of the energy dissipation in high temperature superconductors and how to solve these detrimental defects. Then we will report the synthesis of superconductors and their various structural, microstructural, morphological, electrical, and magnetic properties. So, on a larger scale, electric grids such as higher power lines lose over 20 to 40% of their energy in the process of transmission. So in an electric power industry generated more than $500 billion. That's a tremendous amount of wasted money. So globally, the computer systems of Google, Microsoft, Facebook, and others requires enormous amount of energy to power massive cloud servers and data centers. Even more energy to power water and air cooling systems is required to offset the heat generated by these computers, laptops, mobile, etc. So by using superconductor materials, we will be able to transmit very high electric power over very long distances without any loss of energy or any voltage drop, not like the conventional materials such as the copper. They can be used in transmission cables or in winding for motors, generators, and transformers. For example, superconducting transmission cables will take up less space. For example, here around 100 kilograms of superconducting wires can replace 10,000 kilograms of bandage copper cable. So it's making it over 7,000% more space efficient. And there are many other advantages for superconducting materials. Another example, during the recent years, you all know that the global warming became really a serious environmental issue. The great majority of land transport machines, mainly automobiles, consume large amount of petroleum, either in the form of gasoline or diesel fuel. So to cope with the issues of depletion of fossil fuels and global warming caused by CO2 emissions and realize sustainable motorization, significant improvements in energy efficiency and the shift to non-petroleum alternative fuels are required. So nowadays, the world is oriented towards electric vehicles, which use electricity to deliver power from a motor, realizing high efficiency, high performance motor is the key to the development of electric vehicle systems. So thanks to the recent improvements in the performances of high temperature superconducting materials, the feasibility of more efficient electric vehicle system by applying superconducting motor is being actively investigated. Furthermore, superconductor could be used for some technology based on strongly resonance coupled method that realize large power charging without any wires through the air. We can call as superconducting wireless power transfer for electric vehicles. So the superconducting equipments have a great impact on the economy, such as much higher power density. They can carry tremendous amounts of power, low voltage required for high current. They could be used in storing high amount of energy. There is no power loss during the transmission or the storage of the energy. They are also environmentally friendly, display better lifetime. They need less maintenance, so less maintenance costs. So the high temperature superconductors need the liquid also. They need the liquid nitrogen as cooling medium to work as superconductor. So there is no need for oil. So the utilization of superconducting material is significantly boosted during the recent years. For example, the curves of the motors and transformer based on superconducting materials are expected to reach 70% till 2025. The curves of the use of superconducting generators and cables are expected to reach 50% till 2025. At the same time, the cost is reducing progressively. Who knows, maybe one day we will have electronics that utilize superconductors to give us smartphones or laptops that only need to be charged once a time per year or more. So any more guess, so it is only one guess, but with the rapid advances in our technology, we will all likely see superconductivity in our lives as a regular future sooner rather than later. These are some examples of applications that require higher current and higher magnetic fields than do others. As you can see, extremely high currents and high magnetic field could be only reached by using superconducting materials. For example, the electrical generators made with superconducting wires will be more efficient than conventional generators wound with copper wire. Also, superconducting generators used in the field of winding, for example, can produce also higher currents and therefore higher magnetic field. So superconducting generators have the benefits of small size. Their size and weight are about half that of conventional generators. Also, lower energy consumption than the conventional generators. Their efficiency is above 99% and 50% reduction in input power losses. So a graph illustrates the cost against the power. As it is clear here, the conventional technology costs cheaper when we are dealing with low power level. However, when we are dealing with high power or high energy, the cost of superconductors based technologies is much lower and achievable compared to conventional technology. Here, I summarized some of the important technological application of superconductors, in addition to the previous mentioned examples. So superconducting materials can transport high or huge amount of current with no loss of energy. So they could be used in the transport of energy as well in storing enormous amount of energy, like in the case of superconducting magnetic storage systems. Superconductor can be used also in the production of sensitive magnetometer called squeeze, or superconducting quantum interference devices, which are the most efficient systems to measure magnetic fields with great accuracy, even to detect and measure the Weak's magnetic field. Also, superconducting materials are also used in the production of powerful superconducting electromagnets that could generate stable and very high intensity magnetic fields, which are currently used, for example, in the transportation area, like maglev train or magnetic levitation train. The maglev train that contains superconductor materials will float above an applied magnetic field, leading to eliminate the friction between the train and the rails, and hence the maglev train can travel at very high speed. Recently, 2 years ago, China introduced their new Chinese maglev train, which can travel at a speed of about 600 kilometers per hour. The largest application of superconductivity are in MRI and NMR, which require strong magnetic fields. This can be provided only by using powerful superconducting electromagnets. Superconducting materials are also used in particle accelerators to accelerate particles with a speed near to the speed of the light, like the well-known CERN's Large Hadron Collider. Superconducting materials also can be used in quantum supercomputers, which will lead to a very fast computing calculation. And there are many other important applications of superconductors. And there's still many other fields that can be covered by superconducting. So let's just here talk about the fundamental properties of superconducting materials. So superconducting materials display two fundamental properties. First, zero resistance. So it is a perfect conductor. So superconducting materials have the capability to conduct, as mentioned, enormous amount of current compared to conventional conductors without any loss of energy. And of course, this happens below a certain critical transition temperature. We noted here, for example, as TC0. Of course, this current should be below a certain critical current density. An amazing coincidence phenomena from the discovery of superconductivity is that when a current is passed through a closed superconducting wire, it can flow for a long duration, estimated to be up to 100,000 years. So it can flow without any loss of energy. The next fundamental or important discovery in the field of superconductivity is the Misnsk effect, or in other words, the perfect diamagnetism. Indeed, when an external magnetic field is applied on a superconductor materials, the superconductor will tend to totally expel the flux line from its antenna. Of course, here also the external applied magnetic field should be below a certain critical magnetic field. We noted, for example, here as HC. So, and one of the spectacular phenomena of Misnsk effect is the magnetic levitation that we described just in the previous slide, which is the principal word behind the magnetic levitation train. So here, to summarize, the superconducting state, so the superconducting state is limited by three important physical parameters: the critical transition temperature T, the critical magnetic field HC, and the critical current density GC. Some of our objectives for further improvements in superconductivity research is increasing these three critical parameters by enhancing flux, also by improving the morphological and microstructural properties, by improving superconducting grain alignment and enhancing the conductivity of the grain, and also further reducing the cost of superconducting materials. Here we presented the evolution in the critical transition temperature as a function of the year for the main important superconducting materials. We can classify these materials on the following big families, such as the conventional superconductor materials, which are mostly pure elements or alloys, and the furan, which are based on the carbon 60, and also the pnictides, which are based on the iron. So most of these materials display superconductivity phenomena at the critical temperature below than the temperature of the liquid nitrogen, which is 77 Kelvin. So they necessitate the liquid helium to be cooled and show superconductivity phenomena. One of the interesting family is the cuprate superconductors, which will be the subject of upcoming discussion. They are called cuprate or cuprate oxide superconductors because they are mainly based on copper and oxygen, and their crystalline structure consists of different layers of CO2 planes and CO2 chains. So the well-known cuprate superconductors are the YBCU with the critical transition about 92 Kelvin, and the BISCO with the critical transition temperature around 110 Kelvin. So as it is clear here, these materials display a critical transition temperature above the temperature of the liquid. So they are classified therefore as high temperature superconductors. So to show the superconductivity phenomena, they necessitate to be cooled using liquid nitrogen, which is very easy to be produced, and also it is much cheaper compared to liquid helium. So generally, these high temperature superconductor materials are considered as type 2 superconductor. So these materials displays in their phase diagram a mixed state where there exist normal phases and superconducting phases called as vortices. So the vortices is consist of a cylindrical core arranged parallel to the flux line. And simply the vortex can be simulated as, we can say, as a tornado where the core absorbs everything and the surrounding supercurrents will expel the magnetic field. Under the effect of an applied magnetic field and in the presence of a transport current density, a Lorentz volume force will be applied on the vortices. So this force will put instantly the vortices in motion, which induces a non-zero resistivity and consequently a dissipation of the energy. So once we perform, for example, the measurement of the critical current density versus the applied magnetic field, we find that it decreases rapidly with increasing the intensity of applied magnetic field. So to minimize this detrimental effect and improve the electrical properties of superconducting materials, the vortices must be pinned. And to achieve this objective, the generation of efficient structural defects inside the superconducting matrix could be a possible way. And these generated defects, if they are well distributed, can allow to pin the vortices in their places and thus prevent the energy dissipation. Here we should be careful. Sometimes the defects can also be detrimental to superconductivity. So the art here is how to create good defects for a given application. We can put this one. So one of the useful ways to enhance the superconducting performances of high temperature superconducting materials is the inclusion of nanostructural materials that could pin the vortices by their volume. The interfaces between the nanomaterials and superconducting matrix, as well as these nanomaterials could generate defects within the superconducting matrix, which will contribute to further pin the vortices. Here, the selection of the appropriate nanostructural materials is very important. Briefly, we can say for the synthesis of high temperature superconductor materials, such as the YBCU or BISCO, added with nanostructured materials, we adopted firstly to prepare the precursor. The precursor, it means a compound that do not contain any residue of carbon at the end. To prepare the precursor, different methods can be used in our laboratory, such as the solid state reaction by hand grinding or by means of high energy ball milling. We could also use the chemical routes, such as the salt gel autocombustion approach, cyanochemical approach, hydrothermal synthesis, etc. If we decided to work on nano superconductors, if other forms are preferred, other techniques such as the spin coater could be involved to obtain coated films, or the electro spinning could be also involved if we aim to produce nanofiber superconductor. So here the choice of the synthesis method depends on the final products. Then the obtained superconductor precursor will be grinded, and different amount of nanostructural materials will be added to the precursor. They will be compacted into the form of pellets. Then the different products, either the precursor or the mixed ones, are subjected to different steps of calcination and centering at high temperature. As additive to superconducting materials, we are investigating the effect of different factors related to the nanostructural materials, such as the effect of the shape, such as, for example, nanoparticles, nanowires, and even nanotubes, like in the case of carbon nanotubes. We are also studying the effect of the size. For example, here it is about 100 nanometer for tungsten oxides, 20 nanometer for the magnetic nanoparticles, 30 to 40 for the case of silica and titanium oxide. Also, the effect of the nature and the type of nanostructural materials, such as the semiconductor tungsten oxide and titanium oxide nanoparticles, the insulator for the case of silica oxide, and magnetic nanoparticle for the case of zinc oxide, or others. These are some of the recorded XRD patterns for YBCU superconductors added with different amounts of tungsten oxide nano entities having nanowire shapes and magnetic nanoparticles of cobalt ferrite. As it is clear here, predominantly single YBCU phase with orthorhombic structure was observed in all synthesized products, confirming the successful preparation of desired composition. Also, no noticeable shift in XRD peaks, as well as there is no noticeable variations in the latest parameters. This indicates that the orthorhombicity of material added with tungsten oxide nanostructured materials was conserved with the addition, of course, of small and appropriate amount of tungsten oxide nanostructural entity. Opposite to this example, it is clear here that the inclusion of magnetic nanoparticles affected greatly the different latest parameters and the orthorhombicity, which reduces gradually with increasing the content of additive. So depending on the objective, we can select the appropriate nanomaterials for doping. These are the SEM observation of some of superconducting materials added with the tungsten oxide nanoparticles and nanowires to show the effect of the shape. They showed that the added nanostructural materials with diverse shapes affect differently on the morphology of final product. For example, in the case of nanoparticle added simples, closer looks in SEM images showed the presence of nanometric bright entities of tungsten oxides dispersed and embedded within the YBCO grain. The density of these nano entities increases with the increase of doping content. In the case of nanowires added simples, here we found that tungsten oxide nanowires tend to enter between the grains and to fill the voids between them. And this will provide metal bridges network among superconducting grain. Consequently, the connectivity between the grains will be enhanced and the porosity will be reduced. So here it is expected that the percolation and the transport of the current could be improved much more in nanowires added simples. The inclusion of nanoparticles in high temperature superconductors could generate, of course, also some structural defects. The TM micrograph of YBCO simple added with titanium oxide nanowires showed, for example, here the presence of inhomogeneity as well of structural defects like twins. We present here also an example of the effect of including insulating nanomaterial such as the silica oxide. Interestingly here, the TM micrograph of YBCO simple added with silica oxide nanoparticles showed the presence of nanophases rich in silica embedded within the YBCO superconductor, as well as the appearance of interfaces and columnar defects that could effectively contribute more in the pinning of vortices. For the case of adding magnetic nanostructural materials, we found, for example, that the grain size is reducing greatly with increasing the content of magnetic nanoparticles. So it is evident that the type and the nature of the incorporated nanostructural materials affect in different manner on the morphological properties. Here, there are also some examples for TM images of other kinds of magnetic nanoparticles added to YBCO superconductors, which reveal the presence of relative contrast and high density of twins, stacking fold, as well as the formation of nanophases within the prepared YBCO compound. So such structure could reinforce or strengthen the capacity to pin the vortices. This is also another example from our previous study where we studied the impact of high energy ball milling technique on superconducting properties. We found, for example, that the density of that self-generated nano entities would have a great impact on the superconducting performances. For example, when we make a microstructural observation using TM, it indicates, for example, the generation of crystal defects like cracks and dislocation due to the inclusion of nanoparticles that contribute in the pinning of vortices. So they can contribute to the pinning of vortices and hence lead to further amplify the vortex trapping and improves the superconducting properties of elaborated products. We presented here the electrical resistivity measurements versus temperature for YBCO samples added with a different amount of nanostructural materials having different behaviors. Here, semiconductor for the case of tungsten oxide, and the insulator for the case of silicon oxide. So it is evident here that the different tungsten oxide nanomaterials added to YBCO sample displayed a metallic behavior in the normal state, followed by transition to the superconducting state at a temperature noted here as 0, and the addition of small amounts leads to decrease the resistivity in the normal state, and it do not affect the critical transition temperature. And sometimes, in some cases, we can find a slight increase in the critical transition temperature, of course, for some cases. And this is mostly attributed to the enhanced connectivity between the YBCU grain as revealed before via morphological observation. Considering the case of adding insulating nanomaterials like the silica oxide, we observed metallic-like behavior in the normal state for lower contents, a semi-metallic behavior for moderate contents, and a notable insulating behavior for higher concentration. And this, of course, can be understood due to the nature of the inclusion. And evidently here, the critical transition temperature showed a sharp decline for higher concentration. Here also we present the electrical resistivity measurements once magnetic nanoparticles are included. In this case, the magnetic nanoparticles provoke a rapid degradation in both intragranular and intergranular property of YBCU compound. So here, the magnetic nanoparticle lead also to a reduction in the metallic phase friction and an increase in the semiconducting phase fraction. So the inclusion of magnetic nanomaterial should not reflect definitely that the capacity of transporting high current will be extremely deteriorated. We can pass this one due to time limitation. Here, for example, we presented the measurement of magnetization versus applied magnetic field, which were performed at the temperature of liquid nitrogen, 70 Kelvin. By means of these measurements, the critical current density was estimated using the Bean model. And this parameter is an evaluator parameter to judge if the material is useful for practical application or not. Here, for example, we presented the GC value of one of the examples, such as the tungsten oxide is added to YBCU conductors. And here we found that there is a significant improvement in the absence and in the presence of an externally applied magnetic field with the tungsten oxide nanomaterials addition when we compared it to the Bristol compound. And the enhancement in GC value with nanowires inclusion is by a factor of approximately 4 times or 5 times in the absence of an applied magnetic field, and by a factor ranging between 20 to 25 approximately under an applied magnetic field of 1 Tesla. So the pinning strength is reinforced and strengthened with tungsten oxide nanowires addition. Then we calculated the pinning force from the GC measurement, and the plots are presented in this graph. And different pinning mechanisms were considered according to the Hughes models to explain the phenomena of pinning inside the superconducting materials. Here we found that over the applied field range up to this maximum peak, the normal surface pinning is mostly the dominant pinning mechanism in a Bristol YBCU product. However, in the case of nanowires added materials, we find that there exists a contribution of normal surface pinning and normal point pinning, mechanics. So this indicates that the inclusion of nano entities could enhance the flux spinning capacities by strengthening, by reinforcing the contribution of normal centers in spinning properties. Here we presented the AC susceptibility measurement as a function of temperature, which is useful and practical to evaluate the intergranular properties. Here, the formation of the peak in the imaginary part of AC susceptibility measurement curves is originated from the energy losses caused by the penetration of magnetic fields in the intergranular networks of weak links. So the loss peak amplitude here reduces with the addition of the nano entities. Furthermore, the loss peak shifts to higher temperature with the tungsten oxide additions in comparison to YBCU, to Bristol YBCU compound. And this shift in the loss peak is much slower in the case, for example, here of tungsten oxide nanowires. So these results revealed again an improvement in flux spinning and intergrain and the grain coupling property. And to validate this evidence, we calculated from this curves the intergranular critical current density of simples by means of beam model. Here it is found that the intergranular current density improved with tungsten oxide nano entities addition. So, for example, tungsten oxide nanowires showed the best intergranular critical current density values, and the improvement here is about, when we compare to Princeton compound, is about 2 to 5 times. With the help of SEM and TM observation, as presented in previous slides, and also several other analyses, we established that the improvement in the values of intergranular critical current density, also in the intragranular critical current density and the pinning force, these improvements are mainly attributed to the variations in the composition of the grain boundaries due to the nanoparticles that resides among the grain, to the nanophases implanted in the YBCU matrix, attributed also to the intensification of the interfaces between the superconducting matrix and the implanted nanophases, as well as to the generated structural defect within the compound. So, as summary, we can say that superconducting materials are of great importance nowadays, as well as they constitute a part of a new technology for improving the quality of our life in the future. However, these materials faced some difficulties that limit their wide application, especially the energy dissipation phenomena. We established that one of the useful ways to boost up the superconducting performances of high temperature superconductors, such as YBCU or BISCO, is the inclusion of nanostructural materials. And however, of course, we need to carefully select the appropriate nanostructural materials. The main important features related to these nanomaterials are the size, the dimension, it means 0-dimensional, 1-dimensional, 2-dimensional, or 3-dimensional, the nature or the behavior, as we explained, semiconductor, insulator, or conductor, or magnetic nanomaterials, as well as the shapes and the concentration of doping elements. So the inclusion of appropriate nanostructural materials could lead to improve the intragranular properties and the intergranular properties, which will greatly affect on the performances of final products. So the planted nanophases into the high temperature superconductor matrix, and the intensification of the interfaces between high temperature superconducting matrix and the included or inserted nanophases could play as efficient pinning centers to minimize the motion of vortices. In addition to these, the inclusion of nanostructural materials could generate structural defects that could reinforce the pinning strength of vortices. Of course, one of our perspective works nowadays are to further enhance the superconducting parameters by adopting other methods like deposit enhanced samples in the form of thin films, also prepare superconducting wires and cable for energy transportation. By taking this opportunity, I would like to dedicate special thanks to all our collaborators from around the world, and particularly to those from the following universities for their continuous valuable helps and cooperation in the area of superconductivity. Also, by taking this opportunity, I would like to say that we are open to any kind of cooperation, and these are my emails for any further communication or for any inquiries. And thank you all for your attention.